Okay, the final part of kind of applications of differentiation, as we'll call it, is rate of change. Now, I've already discussed this a few times with you because it's a good way of describing what we actually mean by gradient. Because what gradient is a rate of change, okay? As something increases or as something kind of passes, how much does it increase by? And that's at the end of the day what gradient is, okay? How much does y change with respect to x? And that in itself is what differentiation is, dy by dx. So these things all tie in together, and it leads us to rate of change. Right, there's a few words involved in this which you won't necessarily do much on unless you've done physics. Okay, so you have to get used to some of the wordings here because in an exam it might use these words. Okay, so I'll take you through this first part at least. So differentiating a function, describing displacement. So if you haven't heard of displacement, what displacement is basically how far an object has moved. Okay, so it doesn't have to be an object. We generally, when we're dealing with mechanics and physics and things, we talk about a particle. It doesn't necessarily have to be a particle. It could be an object. It can be a rock. It can be a car. It doesn't matter what it is. But if it's displacement, it's how far it has moved. Okay, it's basically just distance. It's the kind of the vector of distance. And I know that's confusing, but just think of it as distance. Okay. So differentiating a function describing displacement with respect to time, okay? So basically ds, as this would be, d displacement by dt. It can give us a formula to find the velocity of something, okay? Velocity is just speed, okay? Again, it's just a vector version. What it means is that we need a direction as well. That's what we mean when we write it as a vector. So similarly, differentiating a function for velocity with respect to time will give us a function for acceleration. Okay, sounds complicated, but if you follow this, it should be straightforward enough. So if you have a function that tells us displacement, okay, so it'll be y equals, it might be s equals, it doesn't really matter, but it'll be a normal function, just what you've been used to, but it's used to describe how far an object has moved. If you take that function and if you differentiate it, you will end up with a function for velocity. Okay, so in the same way, if you take the function of a graph and you differentiate it, you will find a gradient. If you take the function of displacement and you differentiate it, you'll find a function that will give us velocity. Same idea. Okay, and then if we take the velocity function and you differentiate it again, you'll get yourself a function for acceleration. Okay, and that's all we're dealing with here, and that's all you really need to know. So if you know how far, or in terms of a function, you know how far an object is moving, if you differentiate that function, then you'll be able to understand how quickly it's moving. And then if you take that function and you differentiate it, you'll have a function that determines the acceleration of that thing, that object. Okay. You won't necessarily need to go back the way, but just as before, if we wanted to go back the way, then we would integrate. So if we had a function in terms of acceleration, if we integrated it, we would find a function for velocity. And likewise, if we took our function for velocity and we integrated that, we would get ourselves a function for displacement. All a little bit confusing, but hopefully this example will clear things up. Okay, so an aid package, don't worry about that, is dropped from a helicopter. The distance the package has fallen, so in other words, the displacement of the package after t seconds is given by the function h of t. Don't worry about function notation, but it's basically the function 5t squared. What we want to do is find the velocity of the package 2 seconds after it has been dropped. Right. If I wanted to know the distance it had fallen, I would take my 2 and I would substitute into this because this is a function for distance. But that's not what the question is asking. It's asking for the speed. So I don't have anything in terms of speed yet, so I need to obtain a function in terms of speed. So I need to take my function in terms of displacement and I need to differentiate it. Okay, so h of t equals 5t squared. H dash t will give me the function in terms of velocity. So just as normal, okay, if we differentiate 5t squared, we times by the 2, it gives us 10, drop the power by 1, so it's 10t to the power of 1. Now this function will tell me the velocity after any point in time. Okay, so if I wanted to find 3 seconds, 10 seconds, no matter what it was, I could find the velocity at any point. But the question is asking me specifically for after 2 seconds. So all I need to do is replace my t with the 2. So it becomes 10 times 2, which is 20. Okay. After 2 seconds, the velocity is 20 meters per second. That's it. It's literally it. If you were asked then maybe a part B question to find the acceleration, I would take this function 10t and I would differentiate it again. Okay, 10t differentiated is just 10, so the acceleration is the same all the time. Any of you who've done physics would know that. Okay, but that's not necessarily important here. All you've really got to worry about is that the rate of change. To find the rate of change, we just need to differentiate. But you've known that already because that's what gradient is.